Hi, welcome back. Here we'll be discussing about properties of pure substance. On average, 4 marker question you can expect from this topic. First, I will go through the syllabus, then we will expand and see what are things to be learned. Now I am going to explain the syllabus. In syllabus, we are having thermodynamic properties of pure substance in solids, liquids, and vapor phases. PVT behavior of simple compressible substance, phase rule, thermodynamic property tables and charts, ideal and real gases, ideal gas equation of state and van der Waals equation of state, law of corresponding state, compressibility factor, and generalized compressibility chart. This is all the syllabus is. Now we will see individual components inside the syllabus so that you will be having a good beginning, and after that you can start learning. First we will start with the definition of pure substance. What is actually a pure substance is, and examples of pure substance. You will come to know that air at normal temperature can be considered as a pure substance, right? But you may be a little surprised by hearing that, right? But once you understand the definition, yes, you will agree to my statement. But air at very lower temperature cannot be considered as a pure substance. Why? We will see why it is so when you are learning this. Okay. Thereafter, we will do a simple experiment. We will be taking a beaker of water at an atmospheric pressure and we will be supplying heat. That means heat transfer is being done, and as a result, the temperature of water will increase, right? This is normal thing. Everybody can physically visualize this. And as temperature increases and it will reach 100 degrees Celsius, thereafter we will be seeing boiling, and boiling is followed by vapor formation, right? You know that, right? And we will repeat the same experiment but slightly higher pressure. Now it will be at 2 bar, but remember, we will maintain this pressure 2 bar throughout the experiment. Similarly, we will do this experiment for different pressures, and while doing this pressure we will note what is the temperature and corresponding enthalpy of water or that state, and we will plot this TH diagram, or how the enthalpy is varying with temperature for this water at each pressure. We were doing the experiment at each different constant pressures, right? And finally, if we are plotting that, we will be getting a dome-like structure. What is it? A dome-like structure. And this dome-like structure is called saturation dome for pure substance. So it's a dome-like structure in a 2D diagram, right? And left side you will be seeing a curve that is called saturated liquid line, and on right side we will be seeing a curve that is called saturated vapor line, and on top both will be joining together, right? So we will be having a dome-like structure. Left we have saturated liquid line, on right we have saturated vapor line, and these lines will be dividing the entire region into 3 parts, right? On the left of saturated liquid line, we will call it as compressed liquid or subcooled liquid, and right hand side of saturated vapor line we are having superheated region, and in the middle we will call that region as wet region. Each region is having its own implications, and you will really have a feeling when you are learning this. Then we will go through the difference between sensible heat and latent heat, the definition and understanding of the term dryness fraction, which is the single most important term of this topic. Once we understand this, we will have formula to find the enthalpy or specific enthalpy, specific volume, specific entropy, specific internal energy at a particular point in a wet region using dryness fraction at that point. Now I will be telling a formula for finding the specific enthalpy if we know the dryness fraction at that point. Remember, we are using this formula to find any property at wet region. It is given by, for specific enthalpy, it is given by H is equal to HF plus X into Hg minus Hf. Here Hf is implying specific enthalpy at saturated liquid. We are doing some experiment at constant pressure, right? Similarly, corresponding to that there will be temperature also. So for each temperature and pressure, we'll be having a specific enthalpy for saturated liquid, that is called HF. And various experiments are done, and already scientists have plotted a table for this. So this data are readily available. We don't have to do that. So in an exam, they'll be giving the values of HF and HG. I told you about HG. In this formula we are having HG, right? HG is nothing but specific enthalpy of saturated vapor. Similar to HF, it is nothing but specific enthalpy at saturated vapor line. That is specific enthalpy at saturated vapor line. This is also available in the table if we are giving the pressure and temperature at which we need this HG. So in the question they will be giving this thing. They will be asking you to find what is the enthalpy at particular wet region provided that dryness fraction. You can easily find that. Similarly, the same format will be followed for finding specific entropy, specific volume, specific internal energy also. This is the basis of this topic. On the basis we are doing almost every problem. Then we will find enthalpy, entropy and superheated region also. So far we are discussing about wet region. Similarly, sometimes we will have to find the properties at superheated region also. That also we will be finding. That's very easy part. I am not going to explain that. You will learn when you are going through it. Now we will see ideal gas, perfect gas, semi-perfect gas. When can a gas can be treated as ideal gas? Yes, there was a GATE question and it was asking when we can treat a gas as ideal gas. There were 4 options like high pressure, low pressure, high temperature, low temperature. It is combination we have to choose. Okay, and thereafter we will be seeing van der Waals equation for state, law of corresponding state, compressibility factor and the corresponding chart also. These are all in the syllabus. And we will see various diagrams of pure substance also, that is TS diagram, HS diagram, PV diagram, PT diagram. Earlier I was talking about which diagram we followed initially? Enthalpy temperature diagram. I chosen that diagram because you can easily perceive that. You know that when heat is supplied to water, its enthalpy content will increase. Similarly, we will be having TS diagram, HS diagram, PV diagram and PT diagram. Thereafter we will see what is triple point, and we will see the triple point data for water, CO2, the importance of triple point. Thereafter we will see an important question, that is how a triple point is a line in PV diagram and it's a point in PT diagram. It will be really interesting. I am sure you will enjoy this. If you have good understanding about this topic, scoring full marks from this topic is a left hand job. Only thing is you have to be very much careful while plugging the data from table to the equation. I told you that when we were discussing about that equation, H is equal to HF plus X into Hg minus HF. The HF and Hg value, similarly HF, Hg value and all will be given in the table in the question. But you must be very much careful while you are taking the values to the equation. The possibility of making mistake is huge, so you should be practicing a lot so that you should be having confidence. Otherwise you will be spending a lot of time on solving this problem. 3 to 5 hours of preparation or practice on this topic should be sufficient. You can expect both conceptual and problematic questions, and generally questions used to be straightforward. Knowledge of the topic entropy will be beneficial because I already explained importance of entropy when we were discussing about entropy, right? Now we will see the common questions. I'll explain what are things coming. Questions to find as dryness fraction, internal energy, entropy, enthalpy at particular point in a wet region is a common thing. The same type of question you can expect from superheated region also, maybe combined form also, not direct, but you should be knowing how to do these things. You should have a good idea about isentropic process, and remember, pay very much attention for what I am going to say now. You should have good idea about isentropic process. In most cases, this is the key to the problem. Many times I have seen that People have spent a lot of time on learning this, but sometimes when they see a new problem, they get stuck. But the moment they realize that this particular process is isentropic, they are able to do that. But once they know about isentropic process also, but they are not able to connect immediately. So while doing problems and all, have an eye for that. Now, I told you that conceptual questions can come, right? But conceptual questions can be tricky. So you must